let's get going. So, main thing you guys were covering the last two classes has been Gauss's law, obviously, where the first class on Wednesday you guys were covering mostly what kind of situations?
Yeah.
What kind of situations were you covering on Wednesday
Oh,
with Gauss's
sorry.
law?
Uh, a spherical. I need to say that right because I said spear instead of sphere. Spherical.
Yep. So you were covering spherical situations where you can use Gauss's law. And what are the other two situations you can use Gauss's law in?
Uh, a cylindrical and a plane.
Yep. And why are we able to use Gauss's law in those situations?
Um, Symmetric. There's
Exactly.
some.
Exactly. There's some sort of asymmetry where we can draw a Gaussian surface that follows a few rules. So the first thing is, what the hell is Gauss's law? Like, give me your best explanation of what exactly it is.
uh,
You'll learn to love it.
I hope so. Um. Well, it deals with it in. It helps you trying to figure out the charges of a certain, well, an enclosed space. I think that's the best I can at least say it.
So let's start with the actual formula for Gauss's law. What is Gauss's law?
On the integral of E times dA.
Is it E times dA or
Well, E to the dA, or it's E dA.
um,
dA is in here, and I'm trying to remember if it's supposed to be multiplied or not. It,
I
uh,
pull up the formula sheet
yeah, give me a minute.
right here. I can give it to you here.
That's the full formula sheet. I have like different formula sheets. It's ridiculous.
Oh,
Oh,
yeah,
there it is. Okay. Uh, yeah. So it's the surface, the integral of the surface
Mm-hmm.
dot. Oh, it's a dot pro. Okay, dot
Exactly.
product. Yeah. Okay,
It's
it's not times. It's dot product.
it's a
I was
dot.
just like,
Exactly. So it's a dot product. So what does that
sorry.
mean about?
I'm used to using dots for multiplication, and I just need to remember at times. There are certain times there's. Nope, that's a dot product. That's not multiplication.
Yep. And so that means that E and dA both have to be vectors, right? Because you can't
Yes.
dot product. So it's some sort of an an electric field vector, and we have this area vector. And so it says it's a surface integral. What exactly does this little circle thing on the integral mean?
I think that has to represent a charge. That's the
Not, not exactly.
okay. That was my only guess on that. Honestly, I truly do not know.
So basically, what that means is it is a closed surface integral. So essentially, we have whatever our Gaussian surface is, we have to integrate over the entire closed surface. You can't, for example,
And that's why we get Q enclosed.
exactly. So like for example, if we have a sphere, we can't just integrate over like the top half and ignore the bottom half, or we can't if we have a cylinder, we can't just integrate on. I guess I'll call this the radius. This side here that wraps around, and we can't ignore the end caps.
Mm-hmm.
So our closed integral has to include all surfaces of our Gaussian surface, the entire thing. And so we have this dot product, and it equals, as you said, it was like Q enclosed.
Over epsilon naught.
Yep. More specifically, what exactly is this dot product E dot dA?
Um. Well, when everything's said and done, I believe it just turns into E times A.
Yeah, and more specifically, what sort of what
Oh.
what physical quantity does it represent?
The net, I I believe the net charge. net. It's net of E, I believe. E of net. Hang on.
It has something to do with an electric field passing through a surface. Because that's what this integral is, right? It's the total electric field lines passing through a surface.
Yeah.
So what is that? It has a name. It starts with an F.
Let's see. Did I? The field lines? I don't know.
The word I'm looking for is flux. Does that ring any bells?
There it is.
Yep.
For Rick's sakes, why is it all the way over here? Okay.
Yeah. So electric flux. So what is electric flux?
Oh boy. Why do I keep forgetting these things? Well, then again, it's been a while.
These are the tough questions that need to be asked, and they will help you understand.
Yeah. Uh. Do you need the actual definition of flux?
I mean, just your best understanding of what it is, which might be zero.
It might be.
Give me anything that comes to mind.
Well, flux is supposed to be the total amount of the field lines passing through an object.
Pretty much, yeah. It's the total amount. I'm gonna say that in like very heavy like quotation marks because we're like sort of hand waving a physical quantity. The total amount of electric field that passes through a surface, and that's what the flux is. So it's signified by this like phi thing, and we say phi e specifically because we'll deal with magnetic flux later in the class, and that obviously would be the magnetic field lines passing through a surface. But we'll get to that in like 2 weeks. So
okay. Oh, and that thing's called phi. All right. The pre-lecture has not even said the name of it. So
actually, is it phi or sigma? I can't remember. It's Greek letters. I don't speak Greek, so sorry any Greek people out there. But so we have our surface integral. So we calculate the flux, and by Gauss's law, that equals Q enclosed over epsilon naught. So why do we only get to use this in symmetrical cases? You mentioned something about symmetry.
Well, the one thing is, it is easier to do Gauss's law, but not all cases are going to be like that because if they're not symmetric, it won't turn out it won't work the right way. That's we intended it because it's not all enclosed in that area, I think.
Well, let's think of it this way. If we have, let's say, this is our Gaussian surface. It's this big old sphere that we've drawn. And we have, let's say, we have one charge here and one charge here. Could we calculate the total electric field lines coming out of those charges and passing through the Gaussian surface?
I believe so.
Yeah, we could. We absolutely could. I mean, it'd be a bit ugly, and we'd essentially have to set up some sort of a fancy integral, and it'd probably involve some math that would take someone like me about 10 minutes to wrap my head around, someone like you maybe closer to 30 minutes, but we could do it. We could find a way to represent the field lines going out to each individual point based on the distance from the point, yada, yada, yada. So we could go ahead and calculate this integral. Why wouldn't it be useful for us here? Why wouldn't it be useful for us in the context of this class?
Well, it takes way too much time.
Well, yeah.
Let's see. Oh crap! What are all these popped up? Ah, there we go. Something just popped on my screen out of nowhere.
I guess more specifically, I'll ask, what is the point? Why do we use Gauss's law?
We use Gauss's law to try to figure out the flux of uh the surface.
To then do what?
To find the charge. Honestly, I'm still trying to wrap my head around these things.
Usually, we're given the charge for a Gauss's law problem. We're given the charge, and what's our usual goal with the problems?
Figure out one thing is sometimes figure out the net, but let's see, we're given the charges, sometimes we're given the distance.
Mm-hmm. What's the main thing we're usually trying to figure out?
Enclosed surface? Sometimes we have to figure out the enclosed, so that's what I'm saying.
Well, we create a Gaussian surface to help us with these.
Oh, okay. And we already know epsilon naught.
Mm-hmm. That's just a constant. What
E?
Exactly. We use.
Okay, there we go. Yeah, I was just like, know everything here, and I was like, wait a minute, E.
Yeah, we're using Gauss's law to figure out E, the electric field. Is this going to be easy to figure out the electric field for this example?
Well, in this case, no, but it's still possible.
Exactly. For this case, we would need the electric field to be able to calculate the integral. Versus for Gauss's law, for examples we want that are actually going to be useful, we want to have an electric field that we know is going to be uniform in some way throughout our surface to make the calculation way easier. That's sort of what I was going for. Where we want symmetry because then we can make assumptions to simplify the integral and actually get something useful out of it. So, what are the main things we want from our Gaussian surface? We want our electric field to be somehow uniform throughout it, right?
Yes.
So for a sphere, and we have a charge at the center, obviously that's going to be uniform, right? That's what you guys were covering.
Wednesday.
Yeah, you were covering Wednesday, and we would have covered in our SI Pass session Thursday if I hadn't woken up with a crippling headache. But so that's pretty simple, right? So how would we actually, what's the whole process of actually going for getting the electric field based on, for example, a sphere of charge at the center of a Gaussian surface? What's the sort of general process we go through?
Well, one thing, figure out if it's positive, negative. The charges, anyways.
Yep. Let's assume it's positive, so we know the electric field lines are coming out.
Well, the one thing is sometimes if it's just the one charge, you can figure out since they're all going out in the same direction, magnitude and all that, the net's going to be the net's going to be zero.
Would the net flux be zero?
I'm trying to remember what the name is. It's not the flux. Think the electric field E is zero. Something is zero. That's what I'm trying to figure out. I'm trying to remember. Oh, wait a minute. Is it the Q? It's Q enclosed is zero, isn't it?
But there's a charge right here, right?
Oh, damn it.
I think you're thinking something zero, and I think I know what it is. For this case, we have our electric field lines going out, right?
Yes.
For our Gaussian surface, what direction are our area vectors going to be?
It's going to point out with it.
Exactly.
With the electric field.
Directly outwards, parallel to the electric field. So that means the angle between the area vector and the electric field is zero.
Okay.
How does that simplify our Gauss's law integral.
Well, we don't have to take trig into the account.
So what happens when the angle is 0?
Well, in this case, if cosine 0, it's just 1.
So what's the dot product? It's the magnitudes times the cosine? Is that what you're saying?
Yeah,
Exactly.
I believe so. So we just only need to know the magnitude.
Exactly. So then this integral becomes, it's just a integral of the magnitude of E, I'm just going to leave it as this, times dA. Oh. And we don't have the dot product, we don't have to worry about vectors anymore, because we know that then it would be times cosine of 0, which is just 1 and cancels out.
Mm-hmm.
So, and actually it's still a surface integral. We still need to worry about the fact we're integrating over the whole surface. So it's just E times dA.
Okay.
So then what do we do from here?
Well, in that's the case, we just, again, it still equals to the closed surface Q over epsilon naught.
Well, yeah, we obviously that's still equal. But what do we do to simplify this further?
Well, simplify that further. We can move E out.
Why is that?
Because E is because the magnitude will be constant.
Exactly. So we're able to move E outside the integral. I'm not going to draw the little circle thing anymore, but it's still an enclosed surface integral. Actually, screw it. I'll still draw it. So E times the closed surface integral of dA.
Which I believe it just becomes A.
Exactly. We just have the area of our Gaussian surface. So then we just frickin' divide, right?
Yeah.
So we get the magnitude of our electric field. Remember, magnitude is equal to Q enclosed over epsilon naught, and then what's the area of our Gaussian surface for a sphere?
Well, sphere. Right, that's a sphere, not a circle.
Mm-hmm.
4 pi r squared.
4 pi r squared, exactly. 4 pi, if I can frickin' epsilon naught r squared. Boom. That's our electric field. And then obviously if we want to add our vector quantity back in, just because we know the electric field is straight outward, we can just add a little r hat. Boom. And that checks out with what we know, right?
Yeah.
What's this 1 over 4 pi epsilon naught? Because that's all constant, right?
Yeah.
What's that equal to?
Oh, yeah, that's supposed to equal K.
Yeah, that's K. So we just have KQ over R squared. It's just Coulomb's law. Magic, right? So that's how we use Gauss's law for spherical. And you guys went over that Wednesday and had your quiz yesterday.
Mm-hmm. Well, not yesterday, Friday.
2 days ago. Same thing. It's the last class.
It's in the past.
Weekends all blend into one day anyway. They always feel too short.
Yeah.
So how does this calculation actually change for cylindrical and planar symmetry?
I think only the area changes.
Pretty much, but there's also a few other things we're going to need to do for our integral. And
Okay.
we'll hop in and we'll do some examples. I guess one other thing is, what's the difference between a conductor and an insulator?
Conductors, the charges are able to freely move around, and they will always generally be a net charge of 0. The E would just be 0, the electric field.
Exactly. The electric field inside the conductor is 0.
Yeah, and then the inductors always have a fixed charge. The charges don't move around freely. They're stuck in one position.
Exactly. So insulators, the charges are essentially locked, and hint for this class, all the insulators are going to be uniform. It'll be uniform spheres or cylinders of charge.
All right, cool.
And then conductor, electric field is 0. The charges move around so that the electric field is 0. And then, what's the difference between volume, linear, and surface charge density?
Oh boy. Well, I know. Okay, let's see. They all have their own formula on that one. So I know I have it somewhere. It's probably in my binder. Let's see. Okay. So I believe the linear should be the lambda. So it's the charge over the length.
Exactly. So that's going to be used for lines of charge or long cylinders.
Yeah, that's typically for cylinders. The volume, that would be Q over. Honestly, that'd be Q over V, and I believe the V would still represent volume.
Exactly.
And then the dense, what was it called?
Surface charge.
Again, oh yeah, surface charge density. That, honestly, I don't remember the symbol's name, but that's normally Q over the surface.
Yep, exactly. It's just Q over an area, for example, for an infinite sheet or a conductor, where the charge is all located at the edge.
Okay.
Yep, and the symbol for that is this sigma. So we have lambda for linear charge density. What's the signal? What's the symbol for volume charge density?
Volume. I don't know the name, but it's a P. It's a cursive P, I believe.
Yeah, it's like this weird like P thing. It's called rho.
Rho. Okay, yeah. It's like I know it starts with an R, but I couldn't remember what it was.
Yeah, but it doesn't really matter as long as you know what it is, and if you see it on a quiz, for example, you're fine. So that's the main things you need to know: is conductor, insulator, difference between different charge densities, and actually how to use Gauss's law. So let's go ahead and hop into an example. So we're going to have an infinite uniform insulating cylinder of charge along the x-axis, and we have the radius and the charge density. So it's going to look something like this. Do I have a... Screw it. This is our cross-section. So it's going to look something like this. It's going to be like going off into, infinite directions in both ways. But this is our cross-section. So first thing we want to know is what would be the electric field outside our insulator, and then also what would be the electric field inside the insulator. I'll give you a few minutes to work on it. Let me know when you're done, or just take me through your process as you work through it, because it's just one-on-one.
All right. Well, 1 minute. Alright, this tells me I really need to clean out my binders.
I think I still have my old binders. They're just sitting on my shelf over there. I haven't touched them in... I have one from my sophomore year and one from my junior year. Didn't hold on to any from freshman year, and then senior year was chaos all online, so lots of Google Drive stuff. So how would you start this problem?
I'm just still writing down some of the information.
Good idea.
TM. Let's see. You honestly figure out the best thing is trying to figure out what the charge is at times. If you're trying to figure out the electric field on inside or outside, let's see. So we know the linear charge density is -2 cm. something's causing that to be negative. So my assumption is, if since that's negative, the charge of that should be negative.
Yep. We have a negative charge on our area. What does that mean about our electric field?
That means and normally the linear charge density should be on the surface, I think, so it should be inside. So that means it's a negative electric field, which means everything will be pointing inside.
Exactly. So we're going to have our electric field outside the surface is going to be pointing inward, and also inside is going to be pointing in towards the center.
And I used the wrong symbol for linear, but that's fine. I still got it.
Doesn't matter as long as you use the right thing. So how do you get your electric field outside the insulator? How do you get the actual magnitude?
Ooh. Let's see. The actual magnitude. Well, okay. So, wouldn't it just be 2k lambda over r?
Yep. But how did you get that? I think I know how you got it.
Well, yeah, the formula sheet.
You looked at the formula sheet. How does the formula sheet get that?
How
could you derive that, perhaps using Gauss's law?
Well, let's see. Dang it, I know by Gauss's law that you do get that. I'm just trying to remember the process of getting it. To be honest, I don't remember the process of getting how the formula sheet got it.
So let's just start from our initial starting point, Gauss's law. We have our integral is equal to Q enclosed over epsilon naught.
Okay.
So what is our Gaussian surface going to look like?
Okay, since it's a let's see, since this is a cylinder, I believe in this case should be a cylindrical.
Mm-hmm. Exactly. It's going to be some sort of a concentric cylinder. So it's going to be something outside here, right? And it's going to be some sort of cylinder. How long is our cylinder going to be? How long do we want it to be? Does it matter?
No.
No.
Yeah, it does not matter.
Let's just say it has a length L. And then obviously our radius will be R. That's the radius that we're finding the electric field at. So what would be our enclosed charge inside our cylinder?
Well, we negative.
Mm-hmm.
Yeah, it would be a negative charge due to the linear, due to lambda being a negative number. So, yeah, our enclosed should be negative in total.
Mm-hmm.
I'm trying to still figure. I can understand where they're getting K because of the area with epsilon naught. But I'm trying to figure out where to get the 2 from.
Don't worry about that yet. Just what would our enclosed charge be?
Oh, enclosed charge. Oh, it would be, since it's cylinder, we would need the 2 ends and the barrel. Wouldn't that be it? Or am I thinking a little bit too far ahead?
You're thinking about the area of our Gaussian surface. What's the actual enclosed charge within the surface?
'Cause, 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 That circle.
Well,
I
the
yeah,
circle
this circle.
is just a cross section of our infinite
Oh, right.
infinite cylinder of charge.
All right. So it would just be. Oh, it would just be that portion of the charge.
So how do we get that? What would that end up being?
I know it, but the problem is I'm trying to. Okay.
What's our charge density?
Charge density, linear charge density is Q over L.
Mm-hmm. So if we have that, which is lambda, wouldn't we just have to multiply it by the length to get the total enclosed charge?
Yes. Okay. I was thinking a little too complicated there.
Yeah, it's literally just lambda times the length. That's what I'm looking for here. So then how do we go ahead and find the actually solve this integral? Remember, we have to have our closed surface integral for the entire Gaussian surface.
Let's. Okay, so it will all become. In the end, it will become EA is equal to lambda L over epsilon naught. Our area, I believe the area for this surface would be 2 pi RL.
Well, yeah, that'd be the area of the, how would we say it? The actual like barrel part of our cylinder, but that doesn't include the end caps. So why aren't you including the end caps?
I'm not including the end caps because because there is no charge going through them. There's the electric field is not going through them. Sorry.
Exactly, the electric field. What's the angle between the electric field and the area vector for the end cap?
Uh, they're perpendicular, 90 degrees.
90 degrees perpendicular, they disappear. Boom. So our dot product, our integral essentially, we split it up into three parts. One for each end cap, and then for our barrel. The barrel, it's 0 degrees. Cosine of 0 is 1, so it's just E times dA, which said was E times the area, and the area is 2 pi RL. End caps, electric field, because it's going outward, is perpendicular to our area vector for the end caps. 90 degrees, cosine of 90 is 0. Boom. Magic. That's what I was looking for. I think you had it, you just weren't putting it into words.
Yeah.
So you said it was Q enclosed, so it's equal to lambda L, and then you said our flux is equal to our E times the area, which is 2 pi RL. That's our solved integral, which is equal to Q enclosed over epsilon naught. Right? Lambda L over epsilon naught.
Okay.
Now we just solved.
That all gets simplified to E equals to 2k lambda over R.
Well, does it? We simplify it to E is equal to, see, L's cancel. We have lambda over 2 pi epsilon naught R. That's not 2k lambda over R, is it?
Oh. No, it's not, because we're missing, because it's supposed to be 4, not 2, so that's not, alright.
Or is this 2k lambda over R?
Okay.
What's k again?
K is equal to 1 over 4 pi epsilon naught.
So what would 2k be? 2 over 4 pi epsilon naught, right?
Yeah.
Or in 2 over 4 pi epsilon naught is just 1 over 2 pi epsilon naught. That right there is just 2k.
Oh, okay, so...
Boom. That's how we get our electric field. That's how we get our 2k lambda over r that the formula sheet has. You can get it by using Gauss's law and solving the integral.
Okay.
It's magic, man. And so we know that if we want to add a vector, we know we're going to have to add our r hat. And then we know it is in the... I mean, we don't have to add the negative sign. We know that lambda is negative, so we know it will be in the negative direction.
Yep.
So how would we find the electric field inside the insulator? For example, at this rate, smaller radius r inside.
Okay. Kind of. Isn't it almost the same process, just with a different radius?
Not just a different radius. What else changes? Well, what changes because the radius changes?
Oh, let's see. The length does not matter. Lambda shouldn't be changed. So the only thing I'm thinking would be the magnitude. Wait.
Wait, why wouldn't lambda change?
Yeah, hang on. No, lambda would be the one changing in this case.
Why does it change?
Well, we're going inside the linear charge. We're going inside it, so it would be technically smaller.
Yeah, so we have all this area here is no longer... All this area here plus what's in here is included in the lambda. But now we're only worried about what's in here.
Yeah, so it's basic... Yeah.
So how do we get our new lambda?
Well, you gotta figure out the charge over the length of it. But... Oh, damn, that's gonna be tricky on its own, too.
Well, we know the cylinder of charge is uniform, right?
Well, yes. So... Since that's uniform, the charge is still going to be the same. But the... Wait. If the charge is the same... Length... And didn't we just say the L doesn't really matter?
Yeah.
So,
But there's a smaller cross-section here included.
Oh, so... We just have to figure out the new L along with that to figure out the new lambda.
Not the new L. L doesn't matter, but I'd say let's find the ratio of this cross-section to the cross-section of the entire cylinder.
Okay.
So how would we find that ratio? And let's say, to keep calculations simple in terms of, like, keep it in letters, let's say the original radius here was, like, radius A. What's the original cross-section?
That's what I'm trying to remember right now. That's the lecture one. What happened to my other book? Oh, there it is. I'm trying to remember the stuff for cross sections right now. So,
Well,
our original should be the R, right?
what was that?
Our original should be R, right? The original radius?
We're saying the original radius is A.
Oh, okay, so...
We're going from A to a smaller value R.
Oh, okay. So we're trying to figure out that R is less than A. All right.
Yep.
I honestly don't have any ideas. Nothing's coming to my mind right now. I'm trying for it, but
What's the cross section here? Is what shape is this?
okay. The shape of this cross section right now is uh, I don't know why I keep saying want to say circle.
It is a circle.
Oh, okay.
That is a circle. What's the area of a circle?
Uh, pi r squared.
Yep, exactly. So the original area, so a, we'll call it a naught, is equal to pi a squared. And now a1, what's our area of our new cross section?
Let's see. It's going to be smaller than that, so maybe just pi a.
Well, no, our new radius is r, so it would be pi r squared.
Oh, okay. R squared.
So our ratio of our areas is just r squared over a squared, right?
Right.
So our new lambda, we'll call it lambda prime, is equal to our original lambda times the ratio of our areas, which is r squared over a squared.
Okay.
Does that make sense? Do you have any questions?
Uh, it does make sense. It does make sense.
So now how do we get the electric field inside our insulating cylinder?
Um, well, we will use the same formula as we used last time, but the ratio. Let's see. We'll be using the new lambda prime that we got, and then we also have to use a different radius, I believe.
Which is just going to be r. We'll just leave it as r.
Okay.
And we just know it's going to be smaller than a. So
Yeah.
all we have to do is just plug it into our formula, right? So what do we end up getting?
2k lambda prime over r.
Yep, which then becomes, in terms of the original lambda,
2k lambda r squared over a squared.
r squared over a squared, then we also divide by another r, right?
Oh, okay. So it's just So it's just r over, and then all that is over a squared. Yeah.
Yep, exactly. That's our electric field. We have 2k lambda r over a squared. So that means our electric field, if we plot it as a function of our radius, where here's a, it starts at 0, it linearly increases, and then falls off as a function of 1 over r.
Okay.
Do you have any questions about that? Is that
No, it does make sense. It's just going to take a while for me to keep absorbing this.
Mm-hmm. Yeah, it's a bit annoying to understand conceptually, but if you think about it, it makes sense because each little increment that we increase our radius while we're inside, we're adding more and more surface area. So even though electric field falls off as a function of 1 over r for the cylinder, but we're adding more charge as a function of r squared. So r squared over 1 over r squared over r is just r. Linearly increases. So now, let's say we throw a conducting shell, inner radius 5 centimeters, outer radius 7 centimeters, or just B and C, and we're going to place it concentric to our shell. So it's going to look something like this. We have our inner insulating cylinder charge, and we have this outer concentric shell with an inner radius and an outer radius. Let me expand this further down. Something like that. So let's go ahead and... Oh boy. Let's expand it down and then redraw it. Actually, let's just draw it over here. So we have our inner radius, outer radius. So we have our we have our conducting shell surrounding our insulating cylinder of charge.
Okay.
So how would we get these surface charge densities on the inner and outer edge of the shell?
Well, let's see. The conductor, the charge net itself is 0. The E is 0 on the inside of the conductor.
Exactly.
And then the insulator is still negative on the inside.
So if the electric field is 0 inside here, if we draw a Gaussian surface, let's see if I can I draw this? Okay, boom. Let's say that is our Gaussian surface inside our conducting shell. The red circle is our Gaussian surface.
Mm-hmm.
Electric field is 0 there. What does that mean about the total charge enclosed?
Well, it has to try to equal to 0.
Exactly. The total charge enclosed has to be 0 for the electric field to be 0. So what does that mean about the charge on the inner shell?
Inner shell, let's see. Since the insulator is negative, the thing has to try to cancel that negative out. So that means the inner shell should be positive.
Exactly.
Correct?
Yep. And what would the magnitude of the... Let's start with the linear charge density. What would be the linear charge density on the inner half?
Positive 2.
Exactly. Positive 2 coulombs per meter. And so then what would be the linear charge density on the outer half?
If the electric field still try to go inside it, then I believe... Let's see. I believe, I think that also has to be positive? I'm trying to remember that one. It's trying to go inside.
What's the total charge of our entire shell?
Which one? The insulator or the conductor?
The conductor. What's the total charge of our conductor?
0.
So if...
Oh, okay. So since one side is positive 2, the other one has to be negative 2.
Exactly. So we have the positive 2 on the inner side and the negative 2 on the outside. So how do we go from... That's linear charge density. That's coulombs per meter. How do we go from coulombs per meter to a surface charge density, coulombs per meter squared?
Oh, boy. Okay, surface charge density. So, instead of... Well, we gotta figure out the area. Not this time. Instead of the length. So... Oh. Formula-wise, I'm trying to figure that one out. Let's see. Surface charge density is the charge over the area of the surface.
Mm-hmm.
Let's see. The area of this of... So this is still a spherical thing. Sorry, not spherical. Cylindrical, right?
Yep, it's still cylindrical.
Okay, so the area will still be 2 pi RL. Uh, Actually, yeah, I'm trying to figure out how to get rid of the lambda in order to get the. Well, I don't know, but say get rid of. I mean more like trying to get lambda into the uh charge density.
So let's think of it this way. We'll say this is a sort of a drawing of our inner part of the shell. We're looking at it from the inside.
Okay.
So we're like, imagine it like then loops all the way around like that. So we know that our total, we'll call this a length L. And we know that our linear charge density is positive 2 coulombs per meter. So it's we have a lambda, which is, its lambda is negative lambda naught, but lambda naught is negative, so it becomes positive. So
Okay.
what's the total charge on our entire part of our what's the total charge on the entire part of this inner shell?
The total charge of the conductor?
Yep.
0.
No, for just the inner shell. We're not worried about the outer shell.
Oh, okay. The total charge would just be 2k lambda over r.
That's electric field.
Oh, whoops. Oh, I'm being dumb. It's supposed to be negative. The total charge is supposed to be negative, right? Because it's supposed to be Q over L, and...
So what's Q? It'd just be lambda times L, right?
Oh, dang it. Yep.
And
I
so,
need to put that somewhere.
so we'll call it negative lambda L because we'll leave it in terms of the original lambda, which is on the inside, which is negative. So this is positive, but just roll with it.
Okay.
So that's our total charge. How do we go from total charge to charge per area?
So instead of QL, shouldn't it be, instead of lambda L... Honestly, I don't know. I'm trying to figure that.
So for linear charge density, it's Q over L. What would be a surface charge density? Q over what?
Q over A.
And so what's the area of this part of our inner shell?
The area should be 2 pi RL.
Exactly. The area is 2 pi RL.
Oh, okay. I mean, okay. Keep forgetting. Okay.
In this case,
to figure out what our Q was, we can just put that. Okay.
exactly.
I see.
And so we'll call it B. The inner radius is B, so R is B. So 2 pi BL. L's cancel, so we just get negative lambda. So we'll call it sigma in equals negative lambda over 2 pi B. And that's it. That's our surface charge density. We went from a linear charge density, we found the total charge, and then we divided by the area, and our L ends up canceling out. So what would be the surface charge density on the outer edge?
All right. So that would still be Q over A, and assuming the lambda still sticks in there, so it should be lambda L over 2 pi. And I guess we could still say BL. The L's get canceled out. So
in this case, it'd be C because it's the outer radius. But yeah, you got the right idea.
So it should be this. It should be the same, just a different sign.
Exactly. It's going to be positive lambda, which is negative, over 2 pi C. Boom. That's how we get our surface charge densities. So how do we get that again? Well, we apply Gauss's law. We know electric field is 0. So so lambda on the inside here is going to be negative the lambda of the original cylinder. And then we know the outside is going to be the same lambda as the original cylinder. And then we just we just find the total charge for a length L, and then we divide that by the area in that length L. You have any other questions about this?
Nope, it makes sense.
You sure about that? Are you going to do well in your quiz tomorrow?
Hopefully.
As long as I just keep practicing on it, that really is it.
What sort of grades have you been getting on the quizzes? You've been doing pretty well?
Pretty well. 2 B's, an A, and 2 C's.
It's not too bad. And usually, as long as you average about a high B on the quizzes, and then obviously you do all the homework, you're usually pretty set to get an A in the class.
Yeah, and I hope everybody does this extra credit thing, because that will help out.
Oh, is it one of those things where if 90% of the class does it, everyone gets a 1% boost?
It's 80, but yeah.
Yeah, he likes to do those. Yeah, all right. I guess one more thing. We're pretty much running out of time here because I'm hosting a 21 session in 13 minutes. But let's go over, that was our cylindrical symmetry example. And let's go over a planar symmetry real quick. So we're going to have an infinite sheet of charge. Actually, let's just draw it manually. We have our infinite sheet. Imagine this is a cross section, and we see the infinite sheet going off in this plane, like this. And so we know the infinite sheet has a surface charge density of 6 coulombs per meter cubed, but numbers don't really matter.
Okay.
So what would the magnitude of our electric field be 5 centimeters away from the infinite sheet, like right here? And what about 10 centimeters?
Well, the magnitude would be positive, assuming that the charges are... Yeah, wait.
So what direction is the electric field in? Over here?
That's what I need to figure out first.
Let's see. It's okay, since this is a charge density and it's positive, that means the Q should be positive. That means the electric field should be positive.
Yep, so it's going to be going to the right.
Okay, so yeah, that means the magnitude would be positive.
So what would the magnitude be?
Okay, okay, so which E did I need to... Oh, okay, so I think this time I need to use E is equal to the charge density over 2 epsilon naught.
Charge density over 2 epsilon naught. How do you get that from Gauss's law?
Oh boy, here we go again. Let's see. Let's see, the charge density is Q over A. So, in this case, after everything, it would still be EA is equal to Q enclosed over epsilon naught. Okay, so what's... Oh, crap. What's the area of the thing? That's the...
Well, what's our Gaussian surface going to look like?
Oh, I think in this case it's going to be a cylindrical.
Yep. Let's say it's a cylinder, and how is it going to... Is it going to be something like right here? Where is our cylinder going to be?
It's going to have to go through the plane, so it's going to be from left to right.
Exactly. It's a cylinder with 1/2, so it goes through the plane, one end cap on either side.
Yep, and since we're worrying about the 5 centimeters and the 10 centimeters, we're only worrying about the right side.
Sure. But so what is our electric? So we know our electric field on the right side is going directly to the right.
Yes.
What about the left?
And,
What about the left
the
side?
left side should be literally the opposite. It should be going to the left.
Exactly. So now we have to set up our surface integral for the entire surface. How do we solve our integral?
Well, the integral should still be uh, n on one side plus the n on the other side plus the barrel.
Yep.
But the barrel in this case is 0 because none of the. Wait, is it? Hold up. Wait a minute. I don't think it's 0 in that case.
No, it is. It is. It is. Keep going.
Oh, it. Oh, it's because none of the charges are leaving it. Or wait.
What's the angle between the electric field line and the area vector for the barrel?
Oh, it's perpendicular.
Yep, exactly.
So, okay, sorry. Yeah, I think I was forgetting that I needed to draw those. Oops, that's why I was like, wait, is it 0? I was like, I know I'm forgetting something to determine if that's 0 or not. Okay, it is. The barrel is 0 because the lines are perpendicular.
Exactly. So now, end caps. What does our integral become for the end caps?
Well, one's positive e to the a, the other one should be a negative e to the a.
Is it?
Oh.
I mean, for the right, we have our area vectors going to the right and our electric fields going to the right. So they're in the same direction.
So they're both okay. They're both going to be positive.
Exactly.
All right.
They're both positive. So that means we have 2 times our electric field times our area of our end cap. We'll just leave as A.
Okay, so yeah, it would just be 2EA. Okay.
Yep. So flux is equal to 2 EA, which is equal to, what is our enclosed charge? Within our Gaussian surface?
That's, well, that's sigma, whatever the right way of saying it is.
It's equal to sigma. That's the sigma is a charge per what?
Charge per area?
Exactly. And what's the enclosed area of our infinite sheet within our Gaussian surface?
The cylindrical.
So
So
just
it still would be A.
exactly A, and we just divide by epsilon naught.
Oh, okay.
So then our electric field.
I need to get that to my head that I can change the Q to do that.
Exactly. So then obviously A cancels out, and we divide by 2. So we have.
Because that's going to help me with the homework and quizzes.
So then we have E is equal to sigma over 2 epsilon naught. So does our electric field matter how far we are from the infinite sheet?
No.
Nope, it does not.
So
Wow.
So the magnitude from 5 will still be the same from magnitude from 10.
Exactly. It's always the same magnitude. The electric field for an infinite sheet is always constant no matter how far you are from the infinite sheet.
Okay.
You could be on the other side of the frickin' universe, and it's still going to be the same. Which, obviously, there is no such thing as a truly infinite sheet, because then there would be electric fields everywhere. But we'll see.
Why is my hair taking up these many directions?
What was that?
I was just making a joke, like, oh, why is my hair sticking up in all these directions for some reason?
Yeah. But you'll see examples where you have you're working with an example where you have a sheet of charge that is effectively infinite. You'll see that with capacitors in the next week or two. I think
Oh boy.
it should be this upcoming week. But so then let's say we go ahead and we place an infinite conducting slab, something like this, right here. It's going to be 1 centimeter thick. How would we find the surface charge density on either side of the conducting slab?
Okay. If it's conducting, the net inside the thing's going to be 0.
Exactly.
Since the the left side of it, it's getting, since that electric field is trying to go into it from a positive, the left side of the conductor should be negative.
Mm-hmm.
Which then the right side will have to counteract that, so it needs to be positive.
Exactly. And so how would we get the actual charge density?
Oh boy. Okay, the charge density, we need to get it to Q over A in this case. That would just be, the charge density equals to, wouldn't it just be E, it would just equal to E2 epsilon naught, for our case, or?
No.
No? Alright,
I'll give you a hint. We're going to need to draw a Gaussian surface. Let's draw one side is going to be inside our conductor because we know the electric field there is 0.
Mm-hmm.
And the other side is going to be outside it.
So got it. Okay.
So then we calculate Gauss's law. The barrel obviously is 0 because perpendicular. Yeah. This side is 0 because the electric field is 0.
Okay, so all we just need to worry about is the left end.
Exactly. And then we know that our electric field goes in, and our area vector is anti-parallel. So we add a negative sign. So we have a negative, and it's just 1 EA, because we don't have the 2 from the second side. So we have negative EA is equal to Q enclosed, which is going to be some sort of... So we have Q enclosed over epsilon naught.
And then looking for the charge density, the Q enclosed would just be the sigma A over epsilon naught.
Sigma A times the area over epsilon naught.
And then it would just be E is equal to... Oh, wait. We're looking for the charge... let's start. What are we looking for again?
We're looking for the sigma A.
Oh, okay. So at that point,
it'd just be negative E.
Yeah, you divide
epsilon
A
naught.
and you multiply epsilon naught. Okay.
Which then E we know is equal to negative sigma over 2, because then the epsilon naughts cancel out.
Okay.
And then the other side, sigma B.
It should just be the positive sigma over 2.
Exactly. So we use the Gauss's law, and we do another calculation. That's how we get it. Do you have any other questions about this?
Nope, I just need to do practice, and hopefully I'll do well.
All right. Well, in that case, thank you for coming. Hopefully I won't have any more crippling migraines. Like, seriously, I've never had anything that bad, like, since I had meningitis when I was 6. It was so weird. But thanks for coming. Good luck studying for the quiz tomorrow.
Okay.
Have a good day, Roger.
You too.
See ya.